for the opportunity to speak here. My talk will be about error estimates for the deep Ritz method. And this is joint work with Johannes Müller, who's going to talk after me about a different topic, but related. And today I want to give you a brief introduction to the deep Ritz method, just to recall it or introduce it to you. And the rest of the talk will be about error estimates for this method. And we will start with non-essential boundary value problems. So we will talk about stationary elliptic equations. First, non-essential boundary value problems, and then we will move on to essential boundary value problems, and where the boundary values are treated via the penalty method. And finally, we will discuss some of these error decay rates and how they look in the high dimensional case. So let me recall the deep Ritz method. It was recently introduced, more or less recently, in 2018. And the starting point is that you have a rational energy. So this is some function space here, the x, and there's some energy. And then the idea is to discretize this function space x by choosing a set of neural networks that lie within this x. And then naturally you come up with a loss function that is just defined as inserting the neural network function into that rational energy. And this is very general. These energies can have many forms. I mean, straightforward example from the elliptic case is, say we are on some domain omega in RD. We have a right-hand side f, which is L2, say, and then the space is H1. And this is the Dirichlet energy. Now here also with a lower order term. This could be an example. We will also analyze this, but it can also be different. I mean, it can be an eigenvalue problem where you might use the Rayleigh quotient, and it is very flexible. I will give you another example with a picture. Also, energies that correspond to nonlinear PDEs can fall easily into that framework. Here is an example of the Cahn-Hilliard energy with a gradient term, and here this is a double well potential with its zeros in 0 and 1 in this specific example. And here you see an exemplary implementation of the method. So it seems to resolve this boundary layer quite well. I mean, this is just for illustrative purpose, these examples. So let us start with the error analysis for non-essential boundary value problems. So what we will analyze is the setting we're in for this talk is that X is a Hilbert space. We have a symmetric positive semi-definite bilinear form A, and a right-hand side also in X. And then our energy has this quadratic structure. And in this case, there might be a unique minimizer if it's positive definite, or there might be more than just one minimizer if it's semi-definite. And our strategy tries to mimic what you would do for finite element analysis, for deriving error estimates for finite element analysis. And then the first step is Cear's lemma. So this is what we want to obtain. But we cannot do it in the usual way with neural networks, or generally with the Ansatz classes which are not linear. So let us denote by M the set of neural network functions which lie in this Hilbert space X. So, I mean, implicitly, there is an assumption on how the architecture looks, but for many widely used activation functions in architectures, this is usually, I mean, that we are really in this space. I mean, this could be H1. It must be smooth enough. This is not a problem. And then the first realization is that this set M is not a vector space. And there are two problems. The existence of minimizers of E in this set M is unclear. I mean, the set of neural networks is usually not closed, not convex, so very little. And even if we assume that there possibly might be a minimizer in this M, then because it doesn't have enough structures, it's not the vector space, then we cannot use Galerkin orthogonality. It's in general wrong. So this would be Galerkin orthogonality, and this does not hold. This is, and so I say this is a problem because this would be the usual way to obtain, let's say, a lemma. But we can do something else. And actually, here it's not, I mean, you can think of X and M and E as before, as quadratic energies, but for this slide and for this lemma, X could be a set and M could be any subset and E could be just some function. And then assume we have here D1 and D2. You should think of these two functions as some sort of metric, but you don't need to assume anything. They don't need to satisfy anything for now. And but one thing needs to be satisfied, and this is this two-sided estimate. So assume there is some U star. This will later be the minimizer of the energy. Assume that this estimate holds, so that I can estimate the difference in energy where V runs through all of M, from below by D1 and from above by D2. And then actually we can estimate the distance of V to a U star in the following way. There will be this, there's this delta, which is how well this V approximates the infimum in energy where I run through my ansatz class. So this might be neural networks. This is the lowest energy I could obtain in my hypothesis space of, say, neural networks. And so this measures how well I managed to resolve the optimization. And the second term is an approximation term. How well is my set M, so my networks, how well are they able to approximate a U star measured in D2? And the proof is actually trivial, given that estimate it is trivial because that's what we assumed. You start with D1, you use the first estimate, you insert 0, and use the second estimate. So what this tells us is it should be this estimate what we are after if we want to circumvent Galerkin orthogonality. Some of what is on this slide I already said. So just to recall, the quantity delta is due to incomplete optimization, or measures how well we manage to optimize over our ansatz class M. Then the result shows that approximation rates turn in error decays in the following way. If we know that we have if we can quantify the approximation rate with respect to this upper metric, then we can get the same error decay rate as this approximation rate with respect to the metric D1. In the quadratic setting, that we introduced as our setting before, and which is the relevant one for the PDEs. We can get this two-sided estimate very easily by just computing that these two quantities agree. And here U star must be the minimizer of the quadratic, or one of its minimizers of the quadratic energy. So for quadratic energies, this is very easy to get. And this term here can be translated into the norm of the space X if we assume that A is coercive and bounded. But it is not, this is not limited to the linear case. In fact, you can also use this strategy for nonlinear problems. Recently, we managed to show it for a P-Laplace equation. You can have a look at this preprint here if you're interested in that. But then the derivation is much more technical than this easy calculation here for the quadratic case. And in fact, this is, so now we have some sort of CA's lemma. What is missing again? We're doing it like in the finite element case. Now we need an approximation theorem. So maybe we will talk about an easy example. Let us consider a homogeneous Neumann problem. So the energy that was on the slides before, and if we're using our CA lemma from before, then we get the following estimate. For any, say you have some neural network architecture, it doesn't really matter as long as U theta is in H1 and U star is the minimizer of this energy. Then I can estimate the distance in H1 by this term here. And again, this measures how well we managed to resolve the optimization. And this here is just a question of how fast can neural networks approximate H1 functions. And there are quite some results in the literature which we can use for this this last term here. I have here an example from Güring and Aslan where it says if this U star happens to be in WKP, so has increased regularity, then there is a ReLU squared network with ON many parameters, so that we get this rate here. So now this estimate really turns into an error decay estimate. I will talk a little bit about the rates and what you can learn of them with respect to the dimension D later on. So now we can turn to essential boundary value problems. And here the situation is a bit different, and you have an additional difficulty. And this is that it is in general not easy to enforce your network to have certain boundary values. So I will talk about homogeneous boundary values, but just for simplicity, it could also be any function g here instead of the 0. So and this difficulty comes from the fact that you don't really know which parameters to tune to get this 0 on the boundary, because those networks are some sort of black box. So there are two possibilities, at least two possibilities. So I want to talk about two possibilities what you could do in this situation if you want a 0 here. The first solution is that you would find a smooth function, say I call it eta, which is 0 on the boundary, but is positive inside of omega. And then as an ansatz space for the solution of the problem, you use the product eta times U theta. And then you have to guarantee that you lie in this space. And in fact, then we can also use the analysis for non-essential boundary value problems from before. However, approximation results for this kind of ansatz space are not yet developed to the best of my knowledge. So we can go this step as before with the CA lemma, but we cannot now say what the rates are. Another possibility is penalize boundary. I mean, okay, why you not want to do solution one is that it's maybe very difficult to obtain such a smooth function eta for a complex omega. And what you could do instead is you could penalize the boundary value problems. Say, do we want to solve a Dirichlet problem? Then we have this term, which is the Dirichlet problem, which you would pose on H10, but relax it and penalize the boundary values, including this term to the energy. And then the question is, I mean, then when you solve the optimization problem for E lambda, then you're solving something which is slightly wrong due to this term here. And you would want to know how well does the minimizer of U lambda approximate the minimizer, which I call U naught of the original energy. And our ID in this case was okay. This is the error we are interested in here below, U theta minus U naught. We decompose the error by inserting U lambda, so just a triangle inequality, and treating both cases separately. So the first case here can be treated by, again, by CS lemma, what we developed previously. And this is due to the fact that in this energy, E lambda, we're on H1. There is no boundary values or anything. So this energy is induced by a quadratic bilinear form of H1, which is continuous and coercive. So this term is already taken care of by the previous theory, and then we need to estimate this difference here, and this we will do with a Fourier decomposition. So the theorem that we have in this case is, say omega is bounded and we have a C11 boundary and the right hand side in L2. So maybe you recognize here, this is the setting where we have H2 regularity, and this is what we will need. And M is a subset in H1, and we probably think of that as neural network functions, but might also be just any subset. And here just an abbreviation for the energy norm of A lambda. Then we can estimate the distance of any U theta in our ansatz class to the solution U naught in the following way. So this first term here is again what comes from Sea's lemma, with the delta being how well we resolve optimization on the energy E lambda. With respect how well, just how far we are in energy from the minimizer. And the second term comes from the second term in the triangle inequality. And here we know it goes to 0 with 1 over lambda. And for this estimate to hold, we need U naught to be in H2. I won't go into details here. The idea is that you look at the equation which is satisfied by this difference. And in order to derive a meaningful equation, meaningful PDE that is satisfied by this difference, you need U naught to be in H2 to perform partial integration. And then you can recognize that this is actually a weakly harmonic, and you can use Steklov eigenvalue theory to expand it in an eigenbasis. And this will give you this decay here, which is actually a sharp decay. This term decays this fast, but not faster. So enough of the technicalities. But what is interesting here is that we possibly observe a trade-off in lambda. Just have a look into how this energy norm here looks like. You go to the definition, you see here is a lambda in the boundary integral. So it means inside this infimum, the lambda appears in a bad form for us. We want lambda to be big, but it appears not as its inverse. So there is a trade-off in choosing, or this indicates there might be a trade-off in choosing lambda too big or too little. And this is the fact which deteriorates the error case, as we will see. So let us look into how we would need to choose lambda to get a certain error decay rate. And now we will consider different scenarios. So in general, we make this ansatz that lambda is n to the power of sigma, and we want to determine the best choice of sigma. There are different. Then first assume that we have an ansatz class. It might be neural networks. It might be something else that that can approximate our function U naught, so this is the solution we're interested in, while really having zero boundary values. And assume we have a rate of R for this approximation. Then, in fact, you can show that there is no trade-off, that this lambda, which is here hidden inside this infimum, that you can get away with it because you are approximating with exact zero boundary values. So what you get for the decay rate is then exactly this approximation rate R here. But in the literature, there are no approximation rates with guarantees for zero boundary values. I mean, for example, for a ReLU network, we would know that there are ReLU networks that have zero boundary values, but there is not yet an approximation result that says how fast they are in approximating H1 functions with zero boundary values. So what you could also do is to assume that your ansatz class approximates with a rate in H1 and with another rate on the boundary. And the rate on the boundary will be faster due to the embedding theorems. And then, but we leave it as R and S, then we can estimate our term from above. So here is where the lambda enters, which was chosen as n to the theta. And here this is 1 over lambda. And then we can compute how the error decay looks. The decay of this right-hand side is after straightforward computation this here. So it is the minimum of the decay rate which you have for H1, and this term here for the decay rate you have on the boundary. And then you see that you might end up with a value, with an optimal value rho star, which is slower than than the approximation rate you had for H1. And I summarized this here in a theorem. Now also combining this estimated from above with an approximation result, this time for deep ReLU networks. Now we are in this theorem, we assume a setting where we have a certain regularity, so a CR close one boundary and a corresponding regular right-hand side, so that the solution lies in the Sobolev space with the regularity R+2. And then we can guarantee that there is a ReLU network with a n times this logarithmic term of parameters, and can estimate the error that is made to U0 by here by this term, which quantifies how well we resolve the optimization, and rate n to the minus rho, where rho is smaller than this term here. And some comments on that theorem. So in contrast to the non-essential boundary value case, the error decay above is different from the approximation rate. The approximation rate the theorem yields is, I've cheated a bit here with the logarithmic factor for the ReLU, but for ReLU squared, it would be essentially this. Whereas if we use, so this is the approximation rate in H1, but we get an error decay rate of R plus 3/2 divided by 2D, which is slower, and that's what you pay for the boundary penalty. So far, so good with the rigorous results. I also want to stress that this rate might not be optimal because we don't know yet whether the networks can approximate with the same rate with exact 0 boundary values or not. So that is still open, but so don't take this rate to be optimal, and don't take away from that theorem that it's clear how you should choose the penalty on the boundary, because also in practice we observed that using the boundary penalty deteriorated for large lambda, which you sort of need to guarantee a good boundary, good fit on the boundary, that this deteriorates the training process and makes it unstable, because probably the gradients you get in the energy landscape, they are heavily biased towards resolving the boundary values and at the expense of everything else. So this is just a word of warning in respect to practical implications in this method, but let me talk briefly about how these rates we obtained, what they tell us about deep Ritz method for the application to high dimensional PDEs. Okay, so I would also say this is probably one big motivation for this method to be used in high dimensionals, because in 1, 2, or 3 dimensions with the finite element method, there is already a well-tested method and with good implementations. It works very well, but as soon as you increase the dimension, you run into problems. So first, let's now look into what our rates that we derived in this setting tell us with respect to high dimensions. And for this, I will use again the model problem, the easiest model problem with 0 Neumann boundary values, and this PDE. And I will assume, so we will assume that we are in a setting where we have a high regularity. So let's say you start, the solution to this PDE lies in HK. And then our results told us that there is an n-dimensional parameter space corresponding to a fully connected architecture with a ReLU squared activation, such that we can estimate the distance of our neural network approximation to the true minimizer by this term. So of course, this is always a question: how well can we approximate? How well can we resolve the training process? But here there's the rate, and our takeaway is that if you're in a setting where you have a lot of smoothness, which is, by the way, a very natural setting for elliptic, at least for linear elliptic PDEs, then this can mitigate this problematic dependent of on the dimension. And in fact, the rates you get are also, in a sense, compare favorably with finite element rates. You could get the same rates with finite elements, but then in order to get this rate here, dependent on the regularity k that is available, you would need pk minus 1 elements. So you maybe don't know how regular your solution is, but in order to get the optimal rate at lowest possible cost with finite elements, you would need to choose p to the k minus 1 elements. And also for high k, these elements get a bit they're not so widely used in practice. So, and here for the networks, they're all in one architecture. You don't need to change anything. ReLU adapts, or ReLU squared in this case, adapts naturally to the smoothness you have at hand. And I think this is my last slide. So what you see, this is an experiment where the picture one is so let me describe first what you see here. So on this axis there are the dimensions from 1 to 42, I believe, and here we see the relative L2 error. The problem is the Neumann problem as above, with 0 boundary values, and we have a manufactured solution on the unit cube in d dimensions, and it's the sum of cosine functions and normed to be of L2 norm 1. And then we use a ReLU squared network with 4 hidden layers. So this is implicit here, but increase the width from 16 to 128. And we plot the error, the L2 error, relative L2 error, over increasing dimension. And what you see here is really that that there is no exponential increase in how the error behaves. This is the left slide here. So this is really a plain setup where we just use atom optimization, we just use Monte Carlo discretization. So there's nothing fancy at all. So this is, in a sense, the good properties it has. This is maybe the problematic regime. Now we're here in low dimensions, 1 to 5, and you see here an error which is maybe in the 1 promille regime, but not below. And this is, as far as I know, a general observation that it's hard to train those networks to obtain really low errors. But on the other hand, they seem quite capable of approximating high dimensional functions. So here are my references. They were also below, and I thank you for your attention.